Hello students, welcome back to JCE Connect series of lectures. We'll continue one more design problems on beams. So this particular problem I have taken from a university question paper. So in this problem, what is been given? The internal dimensions of a hall measures 8.5 meter by 14 meter. The concrete roof slab of thickness 120 millimeter is supported by 300 millimeter thick wall all around. The slab rests on I-beams equally spaced 3.5 meter apart and spanning along the shorter side of the hall. Design the beams if the live load is 3 kN per meter square and the floor finishing, that is the finishing load, is 1 kN per meter square. So this is the problem given. So we need to design the beams. So this is the hall dimensions, that is a 14 meter by 8.5 meter, and this entire slab is resting on beams. These beams are of I section, and the wall, that is a bearing, is given 300 millimeter, that is 0.3 meter, and the beams are spanning along a shorter span, that is along 8.5 meter width, and the distance between the beams is given as 3.5 meter. These 3.5 meter, 3.5 meter, 3.5 meter, and the bearing, that is support of the wall, is 0.3 meter or 300 millimeter. So the design steps involves steps for design of beams. The step number 1 will be calculation of load on I-beam. Step number 2, calculation of factored shear force and bending moment. Step number 3, selection of the section. Step number 4, classification of section, and after classification, next will be the check for shear strength, then the check for moment capacity, and check for deflection. So 7 steps. So you just to follow these steps, then design the beams. So in step 1, first you have to calculate the load on I-beam. So you have to calculate load on I-beam. So these are the beams. These are the beam. You have to calculate the load on these beams. So first, the working load W to be calculated in kilonewton per meter. Then self weight of the slab on the beam as thickness of the slab is given, that is 120 millimeter, that is 0.12, multiply by 1 meter per meter we are calculating, into 3.5 kilonewton per meter square load is being given, into this one 25 is what? Density of the slab, that is the RCC. Then we get load as 10.5 kilonewton per meter. This is self weight of the slab. Then the finishing load is given, that is 1 kilonewton per meter square. So if you convert it into kilonewton per meter, that is 1 into 3.5 into 1, that is 3.5 kilonewton per meter we get. Then self weight of the I-beam, it is to be assumed, that is 0.75. Generally it is between 0.75 to 1 kilonewton per meter to be assumed. Then the live load on beam, that is 1 into 3.5 into 3. So live load is given, that is live load is given as 3 kilonewton per meter square. This is the span and this is the per meter. And here also floor finishing is given as 1. This is the span and 1 and 1. Likewise 3 kilonewton per meter square is the live load over a span of 3.5 meter per meter run. So we get 10.5 kilonewton per meter. Then the total load we get 25.25 kilonewton per meter. That is a working load. Then the factor load will be just to multiply it by 1.5. We get as a 37.875 kilonewton per meter. This is step number 1, that is calculation of load. Then in step number 2, you have to calculate the factored shear force and a bending moment. To calculate factor shear force and a bending moment, as we know, for a simply supported beam carrying UDL, this is W, then the reaction will be WL by 2, and the bending moment, that is WL square by 8. This is the moment. So first we need to calculate the span, effective span LE. The effective span of a simply supported beam will be first clear span plus 2 times of bearing length of the beam in the wall. This one. See, this is the bearing, effective span 8.5 meter from end to end, span beam length plus half of bearing, this side half bearing. That will be 8.5 plus 2 into 0.3 by 2, we get 8.8 meter. Then the factored shear force at the end of the beam, that is nothing but a support reaction, that is VU will be WU LE by 2. We know the WU, that is a factored load, into effective span divided by 2, that is the reaction. We get shear force as 166.65 kilonewton. Then next you have to calculate the factored maximum bending moment. So for a simply supported beam carrying a UDL, the maximum bending moment will be WL square by 8 at the mid span. That is factored maximum bending moment at mid span of beam will be WL square by 8. We get as 366.63 kilonewton meter. Okay. In step number 3, selection of the section. For selecting the section, we need to calculate the plastic section modulus required, that is ZP required, that represent the strength of the section. So as we know, MU already calculated. So ZP required will be MU into gamma MO divided by Fy. Substitute in this the values obtained. We get the ZP required is this much, 1613.172 into 10 to 3 millimeter cube. Then for this much of ZP, we need to select the section from steel table or IS 800 2007 page number 138. So in this case, let us try ISWB 450 at 79.4 kg per meter. So here I selected a section as ISWB, and whatever the section you choose, that should give a higher ZP value than the required. The required is this much, and whatever the section you are choosing, that should give higher section modulus. So let us take its properties from the steel table or again IS 800 2007 page number 138. The properties are ZP will be this much, so which is greater than the ZP required. Then note it down the elastic section modulus also. Elastic section modulus, then the depth of the section, then the width of the flange, thickness of the flange, thickness of web, then IZZ, that is a moment of inertia about a major axis, which required when we do the check for deflection, then the root radius of the I section, that is that required for calculation of depth for the section classification. The section will be like this, so you need to take this root radius R1. Okay. Then in section classification, let us calculate first epsilon value, that is the root of 250 by Fy, we get as a 1. Then outstand of flange, that is as per the code it should be half of the flange width, we get as 100 millimeter. Then they calculate the depth of web, that is H minus 2 into bracket TF plus R1. Then calculate the depth, that is we get as a 391.2 millimeter. Then calculate the ratios. So based on these ratios, we can classify the section as a plastic or a compact or a semi-compact or a slender. as per the table number 2 of IS 800 2007. So here the section has a two element. The one is a flange element, other one is a web element. We have to calculate separately the ratios of elements. So let us calculate first the flange element ratios, that is width to thickness. We get as a 6.494, which is less than 9.4, which is this much is a limit for the plastic section. Again, calculate the ratio for the web. We get 41.61, which is less than 84 epsilon. So since both the elements are giving the ratios lesser than the permissible for the plastic section, hence the section is classified as a plastic section. So for a plastic section, the beta value should be 1. And one more check we need to do in the here itself, that is the ratio, that is the thick, depth of web to thickness, that is 41.617, which is less than 67, which represents the check for web buckling is not required. If suppose if it is more than 67, then we need to do for check for web buckling. Then after this, step number 5, we have to go for the check for shear capacity. To do this one, first we need to calculate what is the maximum shear force. Already we have calculated maximum shear force actually acting, that is WL by 2. Then we need to calculate the design shear strength of the section. Section means here whatever the section we have chosen, for that section what is the design shear strength. The formula is VD equal to Fy divided by root of 3 gamma MO into area of web, because web carries shear, hence you have to take the web area, and this formula you get from the code, and we have solved many problems also. So substitute all the values here, we get as 555.044 kilonewton, which is greater than the actual shear acting, hence the section is safe. Then the next, after the calculating the design shear strength, check for high or low shear. So to check for the high or low shear, we need to take the 60% of the design shear strength. So 60% of the design shear strength, when we calculate, we get 333.026 kilonewton, which is greater than 166.65 kilonewton, or the actual shear whatever is acting, which is lesser than the design 60% of the design shear strength, which represents the cases of low shear. So this is of low shear case. Hence for the low shear case, the design bending strength to be calculated, the formula is given. That is the next step will be step number 6, check for the moment capacity. The formula for low shear, that is the section is of low shear, hence the design bending strength will be beta B ZP into Fy divided by gamma MO. Substitute all the values here, when we get 400.134 kilonewton meter. But whatever the design bending strength we calculate for a simply supported beam, it should be lesser than this value, that is 1.2 ZE into Fy by gamma MO. When we calculate, we get the value as 424.936 kilonewton meter, and we have to compare this and this. When you compare both, whichever is the least one, then the value of that MD will be 400.134 kilonewton meter, which is greater than the actual moment acting as 366.63 kilonewton meter. Hence the section is safe in carrying the bending moment. So here we can conclude that the section is safe in carrying the bending moment, since whatever the section we have chosen, it has a maximum moment carrying capacity, where the actual moment will be acting as a 366.63 kilonewton meter. Hence the section, we can say it is a safe, or we can say the adequate in carrying the bending moment. So after this, the next step will be check for deflection. Check for deflection we have to do. This is very, very important. Check for deflection. For deflection check, as we know, for a simply supported beam carrying UDL, this is simply supported beam carrying UDL, then the deflection, this is the deflection, this is delta max. So for maximum deflection, the formula we know 5 by 384 into WL raised to 4 divided by EI. This is a formula we know. First we need to calculate what is the maximum deflection. Here W represents the working load and L represents the effective span in millimeter, E represents the Young's modulus, and I is the moment of inertia of the chosen section. Then the working load, we know 25.25 kilonewton per meter, and when you convert it into Newton per millimeter, it will be 25.25 Newton per millimeter. Then calculate maximum deflection, that is 5 by 384 into WL raised to 4 by EI. Substitute all the values here, that is W 25.25, and the effective span, that is 8.8 meter, convert in millimeter, that is 8800 raised to 4. Then E, substitute value of E, that is 2 into 10 raised to 5. Then the moment of inertia of I section, that is IZZ. Then we get the maximum deflection for the chosen section as 28.12 millimeter for the actual load acting. Then the permissible deflection for the, that is allowable deflection for the simply supported beam carrying UDL will be L by 300 as per the code. Delta equal to L by 300, 8800 divided by 300, we get as 29.33 millimeter. So when we compare this permissible deflection with the actual deflection, delta max will be lesser than the delta that is actually acting. Hence the section is safe against the deflection. Okay, so these are the steps for the design of beam. So very simple, and it's very easy also. So you have to follow the steps. That is, as I said, the step number 1, the first step you need to calculate the load acting on the beam. The second step you have to calculate shear force and a bending moment, that is a factored shear force and a bending moment. And the third is, after calculating shear force and bending moment, you have to calculate the design shear strength, or before that calculation of the design shear strength, you have to do the selection of section. That is step number 3. You have to choose the section. Then after choosing the section, you have to do the classification of the section. Then next, check for the shear strength. Then the check for the moment capacity, and check for the deflection. Okay, and the same problem, if sometimes in exam they may give the same problem, whatever the problem I have taken, this problem. For the same problem, if they said the depth of I beam is restricted to 370 or 350 millimeter, then how to solve this problem? Okay, so here we are not bothered about the depth of the section. We have just taken chosen the section based on the ZP value. Based on the ZP value, we have chosen the section here, this one, based on this value. Based on this value, we have chosen the section in this case. Suppose if the given the depth should not exceed so and so value, so say 350 millimeter or 400 millimeter, should not exceed 350 millimeter, then how to solve that kind of a problem, that we'll see in the next class. So again we'll take that kind of a problem. We'll take the same problem, and the depth is restricted to some value, and we'll see how to solve that kind of a problem. I hope you understood this type of a problem, and please practice this type of a problem and try to understand how to solve. Generally these kind of problems will be asked for 15 to 20 marks. So very, very important problems. Okay, so next class I'll take when the depth is restricted to certain value, how to solve or how to design the beam. Okay, thank you.